So Barak, you're ready?
Okay, thank you very much, Nishant.
Wait, let me at least introduce you a bit.
Sure. Go ahead.
So welcome to the TFR Camp Colloquium, everyone. I would like to introduce Professor Barak Weiss from Tel Aviv University, who will be telling us about geometric and arithmetic aspects of approximation vectors. The floor is yours.
All right, thank you very much, Nishant. Nice seeing you. Nice meeting with everybody, even though I can't be physically present. So this talk will be based on joint work with Uri Shapira, who's mentioned here in the title. And there's a funny story related to my previous visit to India, which was at a conference in Goa, where this was a long time ago, probably more than 5 years ago, maybe more, when this work was already in progress. And Uri Shapira, in fact, gave a lecture about it in Goa, and we had a small room in the hotel where the conference was taking place. The whiteboard was not very big. And Uri said, well, I'm going to give my talk on my iPad. And at that time, that was a very big deal. And the iPad was projected onto a screen, and he just sat there and wrote on his iPad. Well, it's no longer a big deal, but I'm going to use my iPad in exactly the same way. But the results have moved ahead quite a bit since that lecture of Shapira. So here's what we'll be discussing. So we take a real number, which is irrational, and the basic question of Diaphantine approximation is you want to find rationals Q over Q, which are good approximations for X. So a good approximation here means you want to make the difference small, but at the same time you want to make P and Q small. So there's obviously a tension. The larger P and Q, the denser and denser the rationals become. And we're trying to sort of quantify. So to say this a little bit more correct, formally, suppose I fix a number, capital Q, telling me how large can P and Q be. I can ask myself, with that bound on P and Q, how small can I make the difference? So that's the classical question in Diaphantine approximation. And there's a sequence of rationals associated with X. So if you know about continued fractions, you'll immediately recognize the convergence. If you don't know about continued fractions, I'm going to define convergence now, as I call them, the best approximations. So the best approximations, the definition of the best approximations to X, and they're defined recursively as follows. So these are rational numbers, Pi over Qi. Q1 is chosen to be 1. I'm sorry. Chosen to be 1, and P1 chosen to minimize X minus P1. So that means that P1, X minus P1 is less than half. You take the integer closest to X, and that defines P1. So that's the definition of X1 and P1. And suppose we've already defined Q1 up to Qk and P1 up to Pk, then Qk plus 1 is the smallest, so that there exists P, which is going to be Pk plus 1, such that Qk plus 1 and Pk plus 1 is smaller than X minus Pk. So that's the definition of the next pair of numbers, P1 and Q1. And of course, by induction, this is by previous choices, you have this kind of improvement in the quality of the approximation of these numbers. And since this number is less than a half, the PIs, so this difference is less than a half, the PIs are determined once you know the QIs, except possibly you might have two choices in the case of the choice of P1. Okay, so that's the definition. So the PI over QI are called the best approximation. So you can think about this in the following way. So interpretation of the circle, think of the interval 0, 1 as the unit circle, but really I'm thinking of 0 and 1 being identified. This is, I put a metric structure on this, the distance between two numbers in the unit interval is going to be the minimum difference between the numbers. If you define this distance, you can check that it's actually a metric, and what this corresponds to is this is 0, and if x is a point on the circle, and we measure angle in terms of the arc length, and we choose our circle to have total arc length 1, so it's not a unit radius, but a unit circumference circle, then this is just the arc length distance between 2 points on the circle. So this is the circle, and then we have these numbers x, 2x, 0, x, 2x, 3x, etc. These are numbers, points on the circle. So here's x, here is 2x, here is 3x, and so on. And the qx are the QIs. QIs are chosen to give the consecutive minimizers, distance. So the distance from QX to 0. So you keep choosing the ones which are closer than any of the preceding ones, and those are the QIs, and they determine the PIs. And it's not at all hard to check that this requirement here is the same as this requirement here. Okay, so that's the definition of what the best approximations are. And of course, the best approximations depend quite seriously on x. I mean, different x's obviously have different minimizers and different convergents. But the point that I want to make is that there are some statistical properties associated with these best approximations that are the same for almost every x. So I'm going to give examples in this one-dimensional case, which are well-known theorems, and then I'm going to move on to higher dimensions and tell you about some new results. And so the first theorem that I want to mention, so this is the statistics of arithmetic approximations in dimension 1. And so this is a result that's due to local in 2. I apologize for the ringing. Sorry about that. So Mokel proved the following thing. So I'm looking at residue classes modulo m of these continued fractions. So A and B represent congruence classes or classes in Z mod MZ, and there is let's call it P depending on M A B, such that for almost every, so P is a probability, it's a number between 0 and 1, such that for almost every x in the real line, if I look at the pair, so 1 over k number between 1 and k, so that pi is congruent to A mod n, qi congruent to B mod n. This converges to P is equals to. Okay, so I'm telling you the parity, or the more generally the congruence class given a certain modulus n of these convergents, and it's the same for all x's, almost every x. So example, if n is 2, then you have 4 congruence classes. So P congruent to 0, Q congruent to 1 mod 2, P congruent to 1, Q congruent to 0 mod 2, or P congruent to 1, Q congruent to 1 mod 2. All of these cases have probability 1/3 of arising. You shouldn't be confused by the P. P is playing 2 roles here. This is the convergent P, and this is the probability P. So the convergents are going to have one of these 3, fall into one of these 3 categories. You can't have P and Q both even, so you can't have both equal to 0, because if they did, you could reduce the fraction. That would mean P over Q is not a reduced fraction, and it's well known that the convergence always gives you reduced fractions. And so these are the probabilities that you get in the case of congruence classes mod 2 for almost every x. And that's the theorem. The theorem of Mokel asserts that such probabilities exist for every m and every AB, and this is should say that this is very easily computable in all the examples. It's not just, it's very easy to compute what this probability is. Okay, so that's a classical result of Mokel from 82. Theorem 2 is about the statistics of the displacements. We're discussing dimension 1. And so this is a result. It has a long history. I'll say the keywords. It's called the Dublin-Lenstra conjecture, and it was proved by 3 Dutch mathematicians, Bosma, Jaeger, and Weidijk. I hope I'm not saying the names properly. Around the same time that the previous result was proved in 1983, and they proved the following thing. So to find the displacement, the absolute value of this displacement, we'll see the reason for the strange choice of notation in the lecture. The absolute value of the displacement of a pair is defined to be the absolute value of Q times B minus QX. Okay, so what am I doing here? If you recall, I'm choosing my P's and Q's such that this quantity is small. So clearly this quantity is going to 0. And now I'm rescaling by multiplying by Q. So it makes it larger. And the question is, what kind of number do I get? And where is it distributed? It's not hard to see by virtue of Dirichlet's theorem. This is always a number between 0 and 1. And the question is, how is it distributed inside the interval 0, 1? And so here's what they proved. I'm defining a function now. F of t is a piecewise analytic function. It's constant for t's between 0 and 1/2. And it's same constant multiplied by 1 over t minus 1 for t's between 1/2 and 1. So this is f is a density, a probability measure. It's called mu on the interval 0, 1, and the result is that for every x in all intervals alpha beta inside the interval 0, 1, 1 over k number of times I is between 1 and k. The displacement, the absolute value of the displacement of pi over qi x lands inside this interval alpha beta, this tends to the measure of the interval alpha beta is k times 10p. So let's take a few seconds to get used to this statement. It's a classical statement, but maybe not too many people are aware of it. So every best approximation comes with a sort of a normalized number measuring the quality of the approximation. The smaller this number is, the better the approximation is. But it's been rescaled, so it's giving us a number between 0 and 1. So, but the smaller it is, the better the approximation. And then you can say, well, where do we approximate typically? How well do we approximate typically? Sometimes we approximate very well, and this is close to 0. Sometimes not too well, and this is close to 1. And on average, for almost every x, on average, we approximate according to a certain measure. And the measure is given by this density function. So maybe I'll draw the graph. So the graph of the density function. This is 0. This is 1. This is 1/2. This is 1 again. And so the density function sort of looks like that. It's a kind of a piecewise analytic density function that has this shape. So it's sort of a little bit more probable to get values close to 0 than it is to get values close to 1. A striking, interesting corollary of this, if you've never seen it before, is that the expected displacement for almost every x, where displacement expected means I just average all the displacements that I see along the sequence of convergence, is 0.3606, ... It's an explicit number, 1 over 4 times log 2. All right, so that's the theorem about the statistics of these displacements. Maybe this is a good time to ask you if you have any questions, and it's also a good time to say, please do ask questions and interrupt me when I'm not being clear. Okay? Questions about the statement?
Yeah, this is Sivaguru here.
Yes.
I think I missed the definition of displacement. Could you quickly recall? Sorry about that.
Yeah, it's right here. So I have a convergent P over Q. I have the number X. I look at this quantity P minus QX, which is nothing but, it's nothing but this. I just wrote it in different order. This is a small number. Along my sequence of convergence, these numbers become smaller and smaller. I multiply this back by Q. That's this Q here. And I've said without proof that that gives me a number between 0 and 1 when I take the absolute value.
Yeah,
So
thank you very much. I missed that.
Yeah. All right. Okay, so that's the second statistic. And those are two theorems. And by the way, unless I say otherwise in the remainder of the talk, whenever I state a result or a claim that I don't give attribution, then that's a joint result in this new work with Shapira.
So, Barak, can I ask a question? So your first theorem is about how these distributions P and Q are distributed, how P and Q are distributed modulo M. What do we know about its relationship? How does it depend on M, A, and B? Is there anything about that?
So I tried to explain this, hint at this in this example. So
here it's just uniform, I guess.
Here it's uniform on 3 out of the 4 possible residue classes, pairs of residue classes. And the last one, the probability is 0. Not only the probability is, I'm sorry for the notation. Let's call it probability. It's not the same P. Okay. So this guy has probability 0. In fact, not only does that probability 0, it never occurs. And it's a similar story for every M. If M is prime, you just have to remove the case when all of them are divisible by the prime. If M is composite, there's sort of a number of cases which you can easily see give rise to non-reduced fractions, and you remove them, and then your uniform on the rest. That's it. You're muted, Nishant, so I can't hear if you have further questions.
You just want to remove the cases where PI and QI might have a common factor. That's all, right?
Yeah. Then it's exactly, and then it's
Then it's just uniform.
on the rest, exactly.
Okay.
But you see, okay, yeah, enough about that. So in particular, like if you just care about the cues, for example, this is already telling you something interesting. I'm just pointing this out. If you just care about the cues, okay, the parity of the cues, you see that odd cues show up twice as frequently as even cues for typical real number. All right, so in fact, the equidistribution theorem 1 and theorem 2 hold jointly. So I'll explain what I mean by that. What I mean by that is that for every alpha beta is before, every m e with PR is before, for almost every x again, 1 over k number between n and k such that, let's see, so now I want pi congruent to A, qi congruent to B mod m, that's what I wanted in the first theorem, and I wanted the displacement to land in alpha beta. This thing tends, as k tends to infinity, to the product, to PR x mu. Okay, so these, not only do these two events, not only do we know their asymptotic frequencies, but they're independent of each other. So for typical x's, for example, if I only care about parity and I ask myself, does this fact about displacements hold if I only look at those PIs and QIs for which QI say is odd? That's a condition that I can pick up in terms of the first theorem. Well, the answer is yes. It's the same. It's exactly the same distribution. There's no specifying that QI is odd has absolutely no relation on the distribution of the displacements. That's what I mean by this independence. Okay. One further fact about joint. That's what I mean by joint equidistribution. Rather. So one more piece of terminology. Let me put that in different color. When this kind of thing holds, I'll say that, so definition, the classes Pi, Qi, mod m equidistribute almost every x according to this PR, which I think of as a probability measure on pairs of residue classes. And similarly here, when this thing holds, I'll say that the sequence, the displacement sequence, I don't want to give a formal definition of what equidistribution is in a general metric space, but it has to do with, those of you who know it know that you can define it in terms of the weak star topology and weak star convergence of measures, of sampling measures, and that's exactly what I'm doing here, but I just gave kind of an ad hoc definition for now. Okay, so those are all results in the one-dimensional case that I wanted to mention, and now I want to move up to higher dimensions. And in higher dimensions, what we're going to see is that you can formulate theorems 1 and 2 and try to prove them, and you can also formulate another theorem about a third quantity, which I'll discuss. So this requires a norm. So we fix a norm on RD, and we're going to define best approximations with respect to this norm. And vectors in d-dimensional space, I'll try to remember to put a little bar underneath so we remember the vectors. I may forget. So we're defining the best approximations, again, recursively, these are vectors pi in z to the b and numbers qi, positive integers qi, and they're defined as follows. Again, q1 equals 1, and well, let me sort of just write down what we're looking for. We would like this, it's the same quantifiers and everything, but what we're measuring is the quality of the approximation with respect to the norm that we've chosen. Okay. Okay. Another way to think about this is, let me draw the picture in 2 dimensions. The norm defines the quotient. So this picture here, we think of as the quotient r squared over z squared, or the 2-dimensional torus. Using the norm, I can define a metric on this torus. I'll omit the details. And then x is a vector. Here it is. And then you just multiply x and get multiples of x. Look at the multiples of x. Pulled back into this unit square, and you're asking about the consecutive minimizers of the distance to 0. This 0 is the point over here. Exactly the same way. And so this defines a sequence of best approximations, just as before. If you know a little bit about continued fractions, you know that in the 1-dimensional case, the convergents are given by the continued fractions, but in the higher dimensional case, there is no analog of continued fractions that gives you all of these. That gives you exactly the same thing. So it gives you the best approximations. And I'm stressing again that all of this depends on choosing a norm. And in the 1-dimensional case, there's just one norm. It's the absolute value. But in higher dimensions, all of this depends on a norm. So the first theorem is, again, the statistics of these residue classes. In higher dimension. Let's write pi as pi1. These, so now the pi's are integers, and now for any a1, ad, and m, there's this probability depending on these numbers. Such that for almost every x, we have the same result as before. 1 over k number I between 1 and k. And here we have pi, sorry, pi j congruent to aj, c congruent to b. Mod n convergence as k goes to infinity. And once again, this is an explicit equidistribution result. And in fact, PR, note, PR does not depend on the norm. It is the same for almost every x. It's definitely not the same for all x, neither in the high dimensional case nor in the 1-dimensional case, but it's the same for almost every x. So this is the first theorem. The second theorem is about, as you have guessed, displacements. Higher dimension. But now here the displacement quantity is more interesting. It's not a number anymore, it's a vector. So what is the displacement property? We have a p and a q, and we have an x, and the displacement is q to the power 1 over d multiplied by difference between P and QX. So let's compare this to what I had before. So first of all, you see that I didn't put an absolute value on anything. And the reason I didn't put an absolute value on anything is because I wanted this to coincide with the previous definition by just removing the absolute values. Okay, so the previous definition, I'll just write it down. Okay, so these two definitions sort of formally look almost exactly the same, except I didn't take an absolute value, so it's not a number, it's actually a vector. And using, again, this Dirichlet theorem, or its higher dimensional analogs, you know that this is always contained in some compact subset of the Euclidean space. And this normalization is just different. It's sort of, there's a natural reason to do this. Essentially, it's because these, on average, you have q points in a d-dimensional square, and so they tend to be q to the power 1 over d apart. So this is sort of the natural scaling, q to the power 1 over d in general. And then the theorem says, so I'm fixing the norm first. Then there's a measure mu. It depends on our norm such that for any, sorry, for almost every x, we have that the displacement, I'll just write it in this way, the displacement of the convergence equidistributes. This is a measure on d-dimensional. It's a boundedly supported measure, probability measure, boundedly supported probability measure on R to the d, and we get this distribution. Now I want to formulate another. Are there any questions about this statement? I'd like to. Yeah. Sure, go ahead. Okay.
Yeah. So earlier we had explicit descriptions of what these probabilities MDA look like, and what these what was the measure mu, what it was like. Do you have any hope of such a description, or none at all?
Yeah, that's an excellent question, because one wants to actually make computations with this measure. In the previous case, I could compute, for example, the expectation. In general, you'd like to compute things, and particularly like to compute the expectation. So that's obviously something one would want to do. We have a quite explicit description, I would say. Maybe at the end of the lecture, I'll sort of give you a hint on how it's described. But it's described on certain measures on the space of lattices in d plus 1 dimension. And it's the explicit description doesn't make integrals at all easy to evaluate. So I don't see that it could easily give rise to numbers. You could compute with it, but it's quite difficult to do that.
Thanks.
And again, it depends on the choice of the norm. Okay, let me mention another further invariant. Only makes sense when d is not equal to 1. So here it is. So I'm going to define, so I'm given a vector, which I want to write in this form, in z to the n. I'm sorry, z to the d plus 1. So P, as we said before, is a d-dimensional vector. Q is a number. So putting them together, I get a d plus 1 tuple of integers. I think of this as a vector in d plus 1. In fact, it's a primitive vector, which means it's not a multiple of a shorter vector. I want to define a projection, and also Q is non-zero. Sorry, I'm assuming, I haven't said why. I'm assuming that P over Q is a primitive vector with Q not equal to 0. In fact, the approximation vectors that will show up all have this property. Q is not zero, and they're primitive. I'm going to define a projection pi of PQ, and this is a projection from D plus one dimensional space to D-dimensional space, where I think of this D-dimensional space as just being the last coordinate zero. So it's the coordinate plane that's spanned by the first D standard basis vectors. And this is the projection with that image with kernel. Okay, so I'm pushing, I have a vector and I'm pushing vectors. The vector has a non-zero last coordinate, and I'm pushing by adding multiples of this vector until the last coordinate becomes zero. And that's my projection. So I project things along the direction of this particular vector. And now given PQ is above, that I'll write it this way, lambda of PQ, the covolume one, I'll explain all the words in a second, rescaling of the projection. So what are we talking about here? So this is a lattice. What does that mean? It's a lattice in ID, i.e. a set of the form you take a basis of ID, look at all the integer multiples of this basis. This gives you a set, which is called a lattice, and it's of covolume one, namely the determinant of this matrix that you get, absolute value of the determinant of the matrix that you get by putting these VI's as columns of the matrix is 1. So I've defined for you a lattice, what a lattice is, and I'm claiming that whenever you have a primitive vector z to the d plus 1, you can manufacture a lattice of covolume 1 in R to the d. Let me repeat the explanation. You take all the vectors in z to the d plus 1, you project them by adding multiples of this integer vector. Now, it's not hard to see that the image is discrete. The reason the image is discrete is that this projection is defined with coefficients of rational numbers, and we're projecting z to the d plus 1, and so vectors can't get too close to each other. There's a minimal denominator of the coefficients of this projection, thought of as a linear transformation. And then I can rescale it so that it has covolume 1, and this is lambda. So lambda lives. So I'm going to denote by curly x sub d, space which people study SLDR over SLD is the space of covolume 1. Covolume 1 lattices. And this is a nice space. It has a nice topology inherited from this quotient. So the mapping here, as many of you know, is that the identification of these spaces is this way. And so that's why these two spaces are the same. I'm not going into details here, but the point I want to make is that this is a nice space on which you can discuss convergence, and you can discuss Borel measures and so on and so forth. And here's our theorem. So this is the statistics of projected lattices. And again, this is for d greater than or equal to 2. I'll say a few words about that in a second. And it says that there's a probability measure mu on the space of lattices such that the projected lattices for almost every x, the projected lattices these projected lattices where Pi, Qi are the best approximations of x, equidistribute with respect to this measurement. And finally, one more theorem. Theorem 4, the equidistribution in theorems 1 prime, 2 prime, and 3 is joint, again, in the sense that I defined before. All of these quantities jointly equidistribute. So this, why don't we consider d equals 1 in this third theorem? It's simply because the space of lattices in dimension 1 is trivial, it's a singleton. There is no space of lattices. So the question only starts making sense in dimensions 2 or higher. This project was influenced by a very beautiful paper of Wolfgang Schmidt. Wolfgang Schmidt proved that projected lattices for primitive vectors give you, the projected lattices also equidistribute with respect to a certain measure, but the primitive vectors that he chose were simply primitive vectors, all the primitive vectors in a ball of radius t, and we took the limit as t goes to infinity. We do something else. We choose a direction x, we get best approximations, and we're talking about the projected lattices arising from these best approximations. So that's just kind of explaining where the motivation for this theorem comes from. I have a few things to say about the proof, but maybe before that, I'm done with stating all the results that I wanted to state. Are there questions about the statements? Okay, so I'll take that as.
So, Barak.
Yeah.
So about theorem 3, so I think I understand the statement, but is there some more intuition that you can give how of what this is actually, this convergence, what is supposed to mean? I know that this is a vague question, but
Maybe
yeah.
maybe you'll see a little bit coming from the proof,
Okay.
but maybe not. It's sort of hard to. Maybe another answer would be the following. I think it's very nice to start with understanding Schmidt's result first. Our result is a little bit more refined, and there have been other refinements over the last years. One of the beautiful one is by Shapira with Einziegler and Akka, but there have been quite a few refinements of this initial Schmidt result. But what does Schmidt say? Maybe I'll repeat that. So you take, so this is Schmidt. I don't remember the year. You take a large ball. The radius of the ball is t. So it's got a whole bunch of integer points inside. And for every one of these integer points, primitive integer points, you project the lattice z d plus 1 to the ortho complement of the vector. So this is there's a d plus 1 plane, sorry, a d-dimensional plane sitting inside d plus 1 dimensions, and you're just projecting zd. And then you rotate this, so you get a lattice. Okay, the lattice in this d-dimensional hyperplane. It's not a covolume 1 lattice. You rescale it by, you're interested in the shape of this lattice, where shape should be understood as the class of lattices up to homothety and up to orthogonal rotations. For example, you might be interested in the shortest vector of this lattice, or in the covering radius of this lattice, or any other geometric quantity that people associate with lattices. And so you look at all of these, you get a sequence of lattices from all these primitive vectors, and you're interested in the statistics. And Schmidt tells you the statistics. It's actually a very beautiful paper. And we do the same. except our measure actually is not the same as the measure of Schmidt. We don't get exactly the same measure, interestingly enough. And also, we just choose the vectors in a different way. We choose them according to the best approximations of a vector, of a pre-given vector X.
Thanks a lot. That helps.
Okay, great. So I think I just have a very small amount of time. How much time do I actually have to check?
Something like 5 to 6 minutes.
So let me use that.
But you can take a bit longer. Yeah.
Okay, so let me give you one idea. Ideas, I just say idea. And I'll focus on a simple case, which is d equals 1. So let's look at d equals 1. Let's define a 2 by 2 matrix of determinant 1. So this is an element of SL2R. Let's suppose that the vector P over Q, or the rational number P over Q, is the best approximation for X. I'd like to formulate that in terms of space of lattices, SL2R over SL2Z. So let me define a matrix AQ. It's a diagonal matrix. It's got Q and 1 over Q. Oops, sorry. Q and 1 over Q on the diagonal. And it's fortunate that Professor Dani is here because I learned much of this from Professor Dani. It's unfortunate that I may be not doing it justice, so I apologize if that's the case. So you take this is a diagonal matrix in SL2R, and I'm claiming that you can detect the fact that P over Q is the best approximation in terms of these matrices in the following way. So first of all, when you multiply the integer vector PQ first by UX, and then by, which is this upper triangular matrix, and then by AQ, which is this diagonal matrix, I won't carry out the computation. You can do it yourself. So this is an exercise, a very small exercise. What you get here is the displacement in the first coordinate, and you get 1 in the second coordinate. So these two quantities, this quantity, the displacement, is sort of evident in terms of this lattice. So I think of UX Z2 is a lattice, and so is AQ UX Z2. AQ UX Z2, it has a primitive vector with y coordinate equal to 1. So this vector here belongs to this lattice here, and the fact that I have a 1 here, that's the y coordinate of this two-dimensional vector. The second fact, which encodes the fact that this is a best approximation, is there are no non-zero vectors of the same lattice in the square, in the rectangle, in a certain rectangle. So I'll write it out explicitly. Oops. Okay, so I'll draw a picture. Here's the origin in Z2. This is height 1. There's a rectangle here. Looks like that. And on the corner of the rectangle is a vector. And this vector is this vector. This vector is at its endpoint right here. And the rest of the region, this entire region here, contains no other lattice points except for 0. That's just a characterization of the best approximation vectors. And so what I can do now is I can define curly S to be all the lattices satisfying this property. So lambda in space of two-dimensional lattices such that lambda contains a primitive vector with y coordinate equal to 1 with no non-zero vectors. Oops. In minus xx, that's 1, where x is the x coordinate of the vector. So that's a certain subset of the space of lattices. And what we're seeing is that if you take this particular lattice and now you start flowing it by these diagonal matrices, whenever it hits this set curly S, section, it's a cross section for the flow. Whenever it hits the cross off from the hitting locations, the precise value of the displacement. And you can also recover the P's and the Q's. I got a sign saying that my connection was unstable. Can people hear me?
You broke off for a second, but now I think we all caught up. If somebody has a question, they can.
I'll just repeat very, very quickly. So F now is a cross section for the action of AT. AT is this group. Into AT is the minus T. The diagonal group on the space of lattices in 2 dimensions. And the displacements and the best approximations can be read off from the return times to this cross section. So cross sections, for those of you who know a little bit about dynamics, you have a flow on a manifold. It's a one-dimensional smaller object that every orbit hits infinitely often. This is sometimes called a Poincare section. And there are measures on the space of lattices, and they deposit measures on these cross sections. And that's all that's going on here actually in our proofs. We set up this cross section. We analyze the measure. There's a natural measure invariant and ergodic under the AT action, which is the hard measure on the space of lattices. And we analyze the measure that you get on this particular cross section. And from this particular measure on the cross section, we derive all those equidistribution results. And of course, I've just shown this for d equals 2, but the same strategy can be made to work in higher dimensions. And somehow the challenge actually is in this theorem 3, and how do you read off this projected lattice invariant from the cross section. But at the end of the day, the way the proof works conceptually is very, very simple. It's about identifying a cross section for a one parameter flow on a homogeneous space on SLD plus 1R over D SLD plus 1Z, identifying the cross section, identifying the natural measure on the cross section, coordinatizing everything, and making computations with this cross section. And I should also say that reproves those results that were proved in the 80s. It's similar to the strategy of Mokel, but it's a completely different strategy to the proof of this Dublin-Lenstra conjecture, the theorem 2 that I mentioned, was proved by a different method. And so that's also interesting. We get a new proof of that previous result using this method. And it gives this joint equidistribution result for free. Okay, having said all that, this is a good time to stop. Thank you for listening, and feel free to ask more questions.
Let's thank Barak for a wonderful talk. I open the floor for questions. Any questions for the speaker? We had quite a few in the middle, but
Everything was crystal clear. Apparently.
I think it was. Let's thank the speaker again. And
Okay, Nishant, thanks a lot.
yeah, thanks a lot, Barak, for giving this wonderful talk. So
Happy to do it. Okay, great.
hope to see you in Israel in real life soon.
I hope so too. I definitely hope so. Okay, take care.
You too. Bye bye.